How to yo-yo. Follow these steps and you will be spinning tricks in no time at all. You will need a yo-yo and a hand. Step 1. Unravel the yo-yo so it rests on the floor. The string should reach your belly button. If it's too long, cut it where it meets the bottom of your chest when the yo-yo is resting on the floor. Step 2. Tie a loop at the end of the string so that the string is the proper length. Step 3. Hold the yo-yo with your left hand, your index finger over the slot in the yo-yo. Wind the string one time around both the yo-yo and your finger. Then remove your finger and wind the rest of the string around the yo-yo. Step 4. Place the loop on your middle finger between your first and second knuckles. Use your dominant hand to yo-yo, which will give you more control. Step 5. Hold the yo-yo in your hand palm up so that the string goes from your finger over the top to the yo-yo. Step 6. Throw the yo-yo forward and downward, opening with your hand open wide and facing your palm outward. Step 7. Turn your hand over so that your palm is facing the floor and sharply tug the string the second the string is fully extended. Step 8. Catch the yo-yo in the palm of your hand, turn it over and repeat. You are now successfully yo-yoing. Keep practicing. Did you know? The yo-yo did not make its way to the US until 1916, even though its history extends back to 500 BCE.
Okay, so now that we've all learned how to properly yo-yo, I guess the most critical question is, what's this got to do with differential calculus? And, well, you're about to find out, I guess. The idea of a yo-yo is that it's, I guess it's an object that sort of moves away from your hand and back up to it again. And the study of the motion of objects is called kinematics. And so in this video, our last video for our differential calculus unit, we're going to have a look at this particular application of differential calculus. And what it means in kinematics. So you can see on this page here, I've just got some definitions of kinematics. This is just a straight Google search of the word kinematics. You can't go wrong with Wikipedia, can you? You probably can, but anyway, it's probably pretty good. Kinematics is a subfield of physics developed in classical mechanics that describes the motion of points, bodies, and systems without considering the forces that cause them to move. So we're only interested in the actual movement itself rather than what's making them move, I guess. Here we go. I like this. The study of kinematics is often referred to as the geometry of motion. Now, geometry of motion, I think that'll be the name of my prog rock band, I think, because it sounds perfect, doesn't it? Okay, so let's have a little look at what we're going to be covering in this video. I've called it optimization techniques because we're doing it as part of the optimization part, but really it's an application of differential calculus. It's not so much optimization, although that does come into it. So the key terms for kinematics is the concept of displacement. Now, displacement is a slightly different concept to distance. So if I said, what distance has the yo-yo traveled? Well, it's going to travel down and then it's going to travel up again. So there's a distance that's traveled in total. Whereas displacement simply means how far away from a fixed point. Maybe it's how far away from the ground. Maybe it's how far away from an airport. It's the distance away from a point rather than the distance traveled by an object. Now, the function that we normally use for displacement is s, or s of t, or s of x. Okay, so that's displacement. The next one is velocity, and we'll have a look at that in a bit more detail in a second, but no doubt you're already familiar with the idea of velocity being meters per second or kilometers per hour and so on. That's velocity. Normally, we call that v. S of x maybe, or v of x, or v of t often. Speed is a bit different. They're very similar, but speed is effectively velocity without a sign. So those bars there mean strip out the sign, positive or negative, and just leave it as a number. So those of you who have done physics, you'd probably be aware of the word magnitude, which is the size of a number. So speed has everything to do with size, whereas velocity has a direction. So with velocity, I can talk about negative 10 kilometers per hour, and that would mean that I was traveling, let's say, towards the origin, and positive 10 kilometers per hour would mean I would be traveling away from the origin. the fixed point, in the displacement, whereas speed would be just 10 kilometers per hour. And the last concept is acceleration, which normally has, we use A for that, or A of x. And we're not going to look at acceleration in this course, and I'll explain why in a second. But that's basically the trifecta there. So displacement, speed, velocity, and acceleration. And then we've got problems to do with that, I suppose. Okay, so let's have a look at the problem itself. So the yo-yo problem, I say problem, you know what I mean. So the path of a yo-yo is described by the following function. S of t equals 56t squared minus 135t plus 100. Now, let's unpack that a little bit, but going back down a little bit further, where t is time in seconds after release from the hand, and s is the displacement, the distance away from the ground in centimeters. So let me just click over to here, and you can see that this little green yo-yo is going up and down like so. So it starts off, when it sort of leaves the hand, it's leaving with a burst of velocity, right, with a burst of speed. And then as it reaches the bottom of it, it's kind of slowed down until there's no velocity left at the bottom, and then it's coming back up again. It's got all this potential energy, and so it's coming back up again. Okay, so that's I don't know if it's potential. I'm not a physicist. It's probably not potential energy. It's probably, I don't know, some kind of energy from the unwound string. But what I wanted to point out is that although this is the yo-yo going up and down, when we actually graph it, we graph it in a two-dimensional space, I suppose, where this is the height away from the ground, so the displacement, so down there or all the way up there, but this is the time that it takes to do so. So if I stretch out the x-axis, which is going to be the time axis, so if I just go to -1 here, so the yo-yo is just there on the end there, and now I'll change this to something like 5, that'll do. You can now see that the yo-yo is, this is the pathway of the yo-yo of time versus height or distance away from the ground. Now, note, it doesn't mean the yo-yo is suddenly swinging out away from the person. This is not a physical representation of the problem. It's a representation of how, of where the yo-yo is in relation to the ground as time passes. So it's kind of like a stretched out picture of the yo-yo's pathway so that we can make more sense of it. Okay, now we know that rate of change is change in y over change in x. We know that instantaneous rate of change is little change in y over little change in x. If y is the height above ground and x is the time taken, then we've got a distance per time unit. And in this instance, we're going to have centimeters per second. So it is definitely a rate, and you can see that centimeters per second, that rate of change, is in fact the very definition of a velocity style thing. So keep that in mind. We're looking at the rate of change of this parabola. The rate of change as we follow the yo-yo's path is going to be the velocity. So back to the problem. Hopefully all those concepts make sense. I'm just going to finish writing this in because I don't know what happened to the writing. Hopefully those concepts make sense, because if you understand the concepts, the rest of it's really just putting it into practice. And you can see I've got a few questions here, and I'll go through them. So first of all, how far away from the ground does the yo-yo start? Okay, now this is classic. Whenever you see the word start or whatever, that kind of thing, it almost always means when t is equal to 0. Okay, so what we do is we take our displacement. Did you notice did you notice that we used s of t as our function? S for displacement of t means the displacement changes as time passes. So s of 0 is equal to 56 multiplied by 0 squared minus 135. Oops. 135 multiplied by 0. So those two are going to disappear, plus 100. Unsurprisingly, it's like the y-intercept, isn't it? 100 centimeters above the ground. And that would kind of make sense. I mean, I'm pretty average height, or a little bit short, maybe, I'm not too sure. I'm 172 centimeters, so that feels like it might be about tummy height or so. Number two, what is the initial velocity? There's that key word again, initial. So whenever you see the word initial, again, don't forget that it means the start. It means when t is equal to 0, but it mentions velocity. So we're going to do the velocity function, which is v of t, and the velocity function is just the change in rate of the displacement function. So we just need to work out what the derivative of the displacement function is, and that'll tell us the velocity. So if I look at my function, it's 56t squared, so that will become 2 times 56, which is 112, and then reduce the power by 1, so t, minus 135, because t reduced by 1 goes t to the 0, and the 100, the constant, disappears. So we've now got our velocity function of v of 112t minus 135. So initially, t equals 0. So we have v of 0 is equal to 112 multiplied by 0 minus 135, which equals minus 135 centimeters per second. And that's how we can write it. Now, again, that negative makes sense, I think. If we have a look at the drawing again, you can see that it starts with, it's a directional speed. It's 135 centimeters per second. That's the speed, but it's also a downwards directed speed. So it makes sense. Down would be 135 centimeters per second. Sorry, I'm getting a little bit tongue-tied there. So negative implies a downwards. Now, I should just point out really quickly that the idea of positivity and negativity really is contextually what we decide it to be. So it makes sense to be talking about a distance going down towards the ground, and so we make that the negative velocity. But that's because that's the way we've set it up. It could make sense that upwards is negative. It's not usually, but I'm just saying it's always got to be important for you to have a look at the context. Okay, moving on. Number 3, what is the distance from the ground when the velocity is 0? Okay, so we've got another velocity here. So we've got v of t, which is equal to, from the last page, 112t minus 135. And we're going to set that equal to 0. That's when the velocity is going to be 0. And now we're going to solve it. So I'm going to add 112t to both sides to get 135 to both sides to get that. And then I'm going to divide both sides by 112. And I've done this already, so just to save a little bit of time. So it would just be a calculator operation. And it turns out that it's 1.2 seconds away. So that's all right. But we're not asked what the time is. It took 1.2 seconds, but we're not asked for t. We're after s, right? So now we have to substitute in 1.2 for s, and we get, 1.2 for t in the displacement function. I'm sorry, I'm a bit tongue-tied here. 1.2 squared minus 135 times 1.2 plus 100, and that gets us 18.6 centimeters above the ground. So just about 20, just a little bit more, less than 20 centimeters before the ground. So there you go. That's what that means. Question 7 says, what is the distance the yo-yo has traveled? So this is distance traveled as opposed to displacement. So if we have a look at our little function here, I might just pause the old yo-yo. We're talking about the fact that it started here about 100 and went down as far as 18.6. Well, what's the distance that it's traveled? It's going to be that distance there, right? So that's what we're going to do. So we've got this idea of, we've got this point and we've got this point, and we're after the distance traveled, and that's going to be that to that. So distance traveled, feel free to pause and do it and come back to see whether you've got the right idea, is 100 minus 18.6. I'm just rounding everything to one decimal place for this video, which is 81.4 centimeters. There you go. 81.4 centimeters is how far that yo-yo traveled in that 1.2 seconds. Next one, how long does it take for the yo-yo to return to the hand? Okay, so again, looking at the graph, and I just, if I take that away, then you can't see the answers, but you can see that I've kind of evened it up already. But we've got the yo-yo starting here, going down at 1.4 seconds, and then going back up again. So we want to know what this point here is, I guess, in terms of how long it has taken. Okay, so let's just do that. We know what S of t is. It's 56t squared minus 135, t plus 100. And we're interested in knowing what t is when the displacement is 100 centimeters. So I'm going to subtract 100 from both sides, and I get 56t squared minus 135t, which is equal to 0. 100 minus 100 is 0. This is not too surprising if you think about it. So that's going to give me t outside of 56t minus 135 is equal to 0. Therefore, t equals 0. Not too surprising because we know that's where it started. And 56t minus 135 is equal to 0, which means 56t equals 135 by adding 135 to both sides. And now, again, you can just use your calculator and go 135 divided by, sorry, I'm on the wrong page. I have to apologize for that. I'll just switch back. So you can see what I've done here. I subtracted 100 from both sides to get to this point. I factorized out the t there, and then using the null factor law, I can see that t equals 0, and or 56t minus 135 equals 0. That's the end. And then I've added 135 to both sides, and I was just saying that if I then divide both sides by 56, I'd get 2.4 seconds as the endpoint. And that's the answer to that one. And it's not too surprising, I hope. You probably could have used common sense, maybe, although it's good to check that out, I suppose. We know that parabolas are symmetrical. We worked out that it reached the bottom of the turning point was at 1.2 seconds. We know it's symmetrical, so if it took 1.2 seconds to get to here, then it's going to take another 1.2 seconds to return back to the start again. So you'd expect it by common sense to be 2.4, as long as you know how parabolas work, which you should do. Okay. What else we got? Last question, I think. At what time or times is the speed of the yo-yo 89 meters per second? Okay, so we are now given a speed and we need to work out what t is. So we'll start with v of t, which remember is s dash of t. So v of t is the derivative of the displacement function. So it's 112t minus 135. And it says a speed of 89 meters per second. So that has to equal 89. So now I'm going to add 135 to both sides. I get 112t is equal to 224. And I'm going to divide both sides by t. And isn't that lovely? It's exactly 2 seconds. So after 2 seconds, the speed is 89 meters per second. And we're done. But wait, we're not. Because, so I'll put a big warning here. Warning. A speed of 89, I should have said centimeters, sorry, centimeters per second means a velocity of 89 centimeters per second, or if it exists, minus 89 centimeters per second. So we have to figure that out as well. So we will go V of t is equal to 112t plus minus 135 equals negative 89. Add 135 to both sides to get 112t is equal to 46. And now divide both sides by 112 and I get 0.4 seconds. Okay, so there's actually two answers, i.e. at 0.4 of a second and at 2 seconds. Here's the full answer there. Okay, and it kind of makes sense if you think about it. It's kind of basically saying that around about here, the speed is 89 centimeters per second, and it goes down and then it comes up with the same speed. And so the speed here is also 89 meters per second. So here and here, effectively. Or here and here, I suppose. Here and 0.4 is what about there? Yep. Okay, so it's in two locations. So you've got to be really mindful of that. Note whether it's talking about speed or velocity. If it's talking about velocity, then you can take the sign as given. If it says speed, then you need to consider both positive and negative. Okay, I'm almost about to wrap up the video, but I do want to give you a bit of a warning about the textbook. When you try the textbook problems that you've been asked to do, you will see that the questions are written like this: x equals t squared minus 12t plus 11, or whatever. This is an example from the textbook. The reason why they've got it that way is because they're considering horizontal motion of a particle. So a particle might start here, and then it moves along here to this point, and then it returns and goes this way for a fixed point origin, O, that kind of thing. Okay, so it's moving that way, and then it's moving that way. So because it wants to keep the concept of a horizontal movement being x, what it's saying that x equals that the distance away from the origin would be x, and that would be t squared minus 12t plus 11. And so if you were asked to work out the velocity at any point, that would be x dash of t, right? I know that's unusual because we normally use x as the independent variable. But in this case, we're saying the distance away from the origin is dependent on t for time. And so we would say x dash of t, or we would say, weirdly, dx by dt. Okay, we normally have the x on the bottom, but it doesn't matter. It just means d dependent over d independent. Try and abstract your thinking there so you don't get too confused. And that would be 2t minus 12, etc., etc. Okay, so just be mindful of that. But the problems are pretty much the same. It's just that they're using slightly different notation in order to preserve the concepts of horizontal and vertical movement. Good luck.